Well, looks like we're live and such. So we'll just do the usual, making sure. Well, looks like we're live. And so we are. So we should be almost ready. And then we'll have to pop these things back up here, I suppose. It requires some effort. I think this works. No, this will work. Yes, that'll work. There's the chat. Yeah, look, both of them popped up. Interesting. We'll take it. Yeah, it works. That's good enough. Okay. Just the same old volcano stuff. I suppose I should post a link below, but it just switches between the two images. It doesn't do anything terribly interesting. But it's volcanoes, you know. So it's donotgo.com/lava.html. But I'll post the link. Could have done that, I think, fairly easily. See if I can do it now. It's fairly easy, I believe. Just to edit. Well, we'll pretend it's fairly easy. Yeah, there it is. And then I just pop it in here, I think, and that'll do. Yeah. All right, so link provided, just for the hell of it. Except I can't get to the save button. There it is. Okay, save changes, and there, did it. Very efficient. RI. So anyway, I just thought I would go over like kind of like an overview video, but with more storytelling and stuff. So when I was a kid, I was told in school, I remember it on the chalkboard, the drawing of the two waves for light. Okay, the wave going this way and then the wave going this way. And this is electromagnetic waving, this photon thing. And it just went right past me like, no, this is, okay, you can say that's what it is, but I don't think you know what it is. And this is just a story. Because it just creates this problem of the waves being these long things, 3 miles long, 10 miles long, theoretically. Just imaging photons as things was really difficult because how could it be this small and then be this big, as a blob or a thing? And it was called a photon, a thing. It was a clump that had a size, a period, a size. And so my brain rejected all that talk, but I just didn't have enough. I didn't know enough to be able to say, oh, they're obviously full of shit, completely. Or to conceptualize a different. My model was just, like I said, the one seemed correct to me as an understanding was to think of the photon as little things at the beginning and the end of the frequency. They're just little, where the nodes of the waves would be is where there would be a thing, a cannonball, a little bit, and it moves the speed of light. And when you have a bunch of them in a row, that's a photon. Now, so right off the bat, our vernacular, the words we're using are broken. And that's like a 300-year-old mistake. I mean, even though they didn't have the word photon in Newton's time, the light corpuscle was described as a corpuscle, as a thing, as a blob, as a clump, as Feynman would say, and not as clumps at a frequency. So even when they got the idea that it was a clump, right, that it was a thing, a piece of something, a something, their view of the something is that the something is stretched. The something is made bigger or smaller to make a photon. Not that the thing at a distance is always the same, and you just change the distance that the things are from each other. So that would be the biggest piece of. It's really, in a sense, I started this unification theory back when I was 12 years old. in grammar since sixth grade. Like I said, I remember it in sixth grade. I remember it on the chalkboard. My first introduction. And later in high school, of course. But really perverted science teacher, actually. It was really weird. Anyway, I might have been traumatized. I have some sort of blocked memories, I think. Anyway, I can't remember his name, but I think he did get arrested eventually for, bad touching. But anyway, where was I? Okay. So in all of these descriptions, I've never really seen anywhere else where somebody says, no, photons are little bits at a frequency, like bullets at a frequency. Really simple to visualize that. All the bullets are the same. They're just, the only thing you can change is how close they are to each other, how far apart they are. But they're all just bullets. Because it's always, like I said, if it's envisioned as a particle or a clump, it's envisioned that you stretch the bullet. The bullets get longer or the bullets get shorter, which doesn't really work. And I had that same problem in thinking about it when I was a kid, that I just really couldn't make the idea of a photon that could be very long. It's really always hard to kind of work. But I mean, I tried to, just because I was sort of prejudiced by the verbiage. The word photon kind of makes you want to make it one thing, when in fact the photon is really 2 or 3 or 4 or 10 things in a row. Which brings me to my polarization argument, which I think is also very intuitively sensible. That what polarization is that, say, these are the bullets, bullet 1, 2 for you, 1. What doesn't really matter? They're moving this way together. These are the bullets. And polarization would just be how much out of alignment they are with each other, which I thought was also a clever. That was a new thing. I didn't think of that when I was a kid, but it does sort of work as an explanation for the polarization of light. So anyway, watching one of Feynman's old videos, where he's basically arguing what is a photon, or explaining, and his explanation kind of just goes all kinds of directions. He just vaguely says these are the properties. Now, he says clearly that Newton was right, that it's a corpuscle, the thing, but Feynman doesn't really explain whether it's a thing like cannonballs at a distance from each other, or whether it's a thing that itself stretches. So we don't have an explanation from Feynman whether his vision was that a photon is something that stretches to different sizes, or whether a photon is just corpuscles at a distance. The implication is that he believes it's a stretchy thing, because he doesn't account for the fact that we have the word photon, and it's really, you have to have at least 2 for it to be registered, for it to be seen or sensed or on a device. The device can't see it if it doesn't come at the right frequency, which is important. All of our devices only sense this stuff when you tune it. We can only, unless you send such a huge volume of it that you can sense it as just an electrical impulse. So the weakness of light, in the sense of it looks like it's a lot of light, but by comparison to other forces, it's kind of a weak force. And there's a lot of light in this room, but it doesn't move me at all. It doesn't, barely even warms me, but it seems like a lot of force, a lot of energy. But it's a minute amount of energy compared to the weak force, gravity, and the strong force, magnetism. Weak, quote unquote, because it's not very weak. But I want to get off the subject. but it really is the subject, because it's, if Feynman's correct that it is a corpuscle, a clump, it's not much of a stretch to say, no, the photon isn't a clump. The clumps are in the photon. It makes the photon, the little clumps. And once you do that, then you can use the same little clumps to do your virtual force for magnetism and to do gravity, just by polarizing it for magnetism. So anyway, he asserts quite aggressively that, yes, Newton was right for the wrong reason, in the sense that he says Newton was correct to observe that shadows aren't cast. Waves would go around objects, therefore waves would spread and they would fill in the shadows. And shadows aren't filled in, just on the mere edges. So again, we have a surface phenomenon, right? So in a sense, he's conceding through that argument that shadows do have a fuzzy edge, and they have a fuzzy edge. Why? Okay, so that would have been the right question to ask, because we've heard about single slit causing fuzzy. We hear about double slit causing spreading, fuzzy. But the truth is, all surfaces create a little bit of fuzz on the edge. The light that goes closest to the surface spreads and creates a fuzzy edge by fanning in to the shadow, by being deflected. So, the important word, deflected. We have all kinds of words. We have reflection and refraction and diffraction and divergence, but they're all just, in a sense, deflections. They're all just the idea that something comes in heading one way, it interacts, and something leaves going some other direction. Deflection. Yes, I'll write that word down. And so all of those phenomenon, reflection, refraction, diffraction, can all be understood as just a kind of deflection, a kind of interaction that causes an angular change in the direction of the photon. And that Feynman would argue that in every other circumstance, when photon doesn't encounter one of these circumstances, the edge of something, photons travel straight. So the ones that don't go close to the edge just go perfectly straight. And it's only the ones that get close to this thing that hook a little bit. Some of those, not all of them, just some of them. So anyway, he says Newton was right for the wrong reason to call it a corpuscle, but in a sense, it's not a wrong reason. Newton is correct. Feynman concedes the point that calling it a wave is sort of wrong, because it's very much unlike a wave in that it doesn't go around anything. If it were a wave, it would go, especially the further away you got to the end, it would go, the wave would spread and it would fill the surface. It wouldn't be a ray force, it would be a wave force. So this would be another important word. Rays aren't used by physics much anymore. Now, rays were said a lot when I was in school. You heard a lot about rays of radiation and rays of force and rays. And somehow that word has lost favor, and nobody uses it anymore. But it's a very important word in terms of understanding that if Feynman did the obvious, which is say, well, if it's not a wave, what is it? Well, then it's a ray. Okay, now we can understand it's a little straight line. It's a ray of something. And for it to go some new direction, what happens to that ray is it's got to bounce off something. It's got to hit something. It's got to be disturbed by something. And so again, these are points I think Feynman would concede. He drew it on the board at one point in his lecture. Photons travel from point A to point B in a straight line. And all of this fancy mathematics is basically just acknowledging that, except when it hits an electron. that's when the mathematics has to get fancy. The photon going about its business isn't doing any of this quantum strangeness. The quantum strangeness only turns up when you put the matter, when you put the force next to the matter bit, when you go around the edge of something. The surface. So another key word in this whole conversation is that what is a surface? So this is where Feynman, I think, sort of dropped the ball, because he would talk about surfaces of glass and how you could polish them, and surfaces of lenses and different things. And yet there was no recognition that what's that surface made out of? It's made out of atoms, atoms that are tightly held to each other. Glass is hard, it's not a, it's not at all mushy, it's hard. And there's a distinction between the lens and the air. And there's a line there. What do you call it when they talk about going from one surface to another? There's a transition. So that's another word to use here, transition. Between a refractive index change. And this is important stuff. But why is that? Why is there that thing? And how does how do we visualize the difference? I mean, an atom isn't a solid thing. It's not a little, it doesn't have a smooth surface. It doesn't have a surface. It has electrons and protons. And the atom, we know, can have other, it can be charged, so to speak, and then it can have an imbalance in its electrons and protons in certain positions. It can reveal that. So if I take a piece of iron and I have all of the imbalances going in different directions, it will express the same magnetic character as this glass lens. That is, it'll have no magnetic character. So the atoms have a lopsidedness, but if the lopsidedness is randomized, that is, it's not organized, it'll express no magnetic character whatsoever. But if I expose it to a magnet and line up those little lopsided atoms, so now their lopsidedness is all in a row, then it will be now a magnetic object. And you could theorize that maybe if the atoms inside a glass could do that also, if they were in a less rigid configuration. Glass is an insulator, by the way. Okay, it does hold charge on its surface. On its surface. Why is it on the surface, the charge? Why can't the charge move through the glass? See, that has to do with the geometry of the glass. The reason why the glass is transparent is because of its geometry. If you could change its geometry, then it wouldn't be necessarily transparent. You could make it opaque. So the reason why it is transparent is because everything has to line up a certain way, and it can't realign to become magnetic. But clearly its surface can do something very different than its interior can do, because its surface has exposed electrons. They're not bound to each other. The atoms aren't glued to each other. So there's no glue on the outside of the lens. There's only glue on the inside. And another, really important when you're going to talk about what happens to a photon when it hits a surface. So he does a whole conversation about how this is why we believe this, random crap, this probability stuff. And it's all based on a very undetailed model of the true interaction between this thing and, the photons and the surface of the material. It's like the two there's no visualization of what that actual interaction is like, because that interaction is actually a nuclear interaction. The photons hitting the electrons, it's hitting the components of atoms. It's not hitting atoms themselves. And it's interacting in specific ways based on the condition of the atoms it's hitting, what the surface is, whether the surface is shiny, whether the surface is consistent, whether the surface has a consistent geometry. And we know if this surface doesn't have a consistent geometry, that the surface becomes incredibly opaque, that the photons end up going all over the place. They scatter, and we see it as having a color because of that scatter and because of the nature of the material, the chemistry of those surface particles, what they're made of. They'll reveal what they are, in a sense, by their color. Like, poo is brown, carbon. Things have a color because of, for real reasons. And some of those reasons are directly related to their chemistry. Their chemistry gives them their color. Oxidation of copper, different things. The consistent color produced by a consistent chemical that's placed on the surface and causes the photons to be absorbed or reflect based on this chemistry they're hitting, the electrons, and how much pressure they're under. So now the next step that just makes this so really important is understanding that their physics, their quantum mechanics, has no model for how photons exist, as how they're created, where they and how they get absorbed when they're absorbed, what they're absorbed as, how they're held inside of atoms. They just don't really have any mechanism at all. They have some notion that photons are somehow interacting in such a way that they might be managing the repulsion and attraction between electrons and protons, but there's only a vague notion that it might have something to do with that there might be some exchange of photons that happen when electrons separate from protons, or when electrons separate from electrons even. But it's just some notion. And if you took it seriously, this kind of a particle idea, and understood that the electrons and the photons are different things, but they have a similar property in that the photons have an affinity, let's say, for electrons. They're very reactive to photons. And so you could it doesn't take much work to say, well, what if the photons are critically important to what's called charge and voltage, in the sense of it decides how close electrons, how much electrons repel each other, how much pressure they're under, how fast the electron will leave when it leaves. Is all going to be decided by how much stuff is between them, bouncing back and forth. And I've used this analogy, and it's a perfectly functional, in my opinion. So yes, by the way, I mean, this is in a sense like the question videos. If you have any facts that say this can't be, because they keep saying it can't be, there's no particle model that can do this, that can explain this. And of course, I think it can fit all of the evidence. All you have in these surface experiments, the two slit, the single slit, Newton's rings, the interferometer, is surfaces. Surfaces is the common thing. And what you have in all of the math is a common angle, a sine theta. It's an angle. It's not a wave. It's an angle. And it's just an angle at which the photon is deflected based on the energy going in, the energy of the photon, and the voltage, the charge potential of the specific electrons of the material you're interacting with, in combination with the charged electrons. As pointed out, this glass surface can have a charge on it, and it can hold it. And it can be even hard to get it off because it sticks all over the place. It's not necessarily directly connected very well. And those are just a representation of the fact that there's a collection of electrons on the surface that there's more electrons in the surface and less protons. The protons are further from the surface and the electrons are closer to the surface. Some analogy like that. And that's the negative charge. And the positive charge would be the inverse of just having fewer electrons in the surface and more. The protons are closer to the surface, electrons are less close to the surface. And that would define charge. But, they're all related, because obviously this is a unification theory, and yes, it's all connected. But I don't really want to confuse the subject of photons with the subject of other things, the other forces. But we're sort of getting to a point where you almost have to do that. So the point is that as I've analogized, you could have two electrons in positions, and we say they're charged, negatively charged. They have a negative charge of 1, okay, as the proton has a negative charge of 1, one quanta of charge, one amount of. But the truth is that the charge of the electron is essentially going to be dictated by how much stuff is in between them. So the little photons, the little cannonballs that would be photons, are essentially bouncing back and forth between the electrons. They reflect off the surfaces. And you can understand that the closer I bring them, the more impacts there are. And it's the impact that is the expression of energy. There's no energy while the photon is traveling. There's only energy when it's hitting. And obviously I increase the number of hits for the same, it's going always the same speed. So I can't change the speed by making my fingers further apart. I can only change the time it takes, but I won't change the impact. So the corpuscular nature of light is maintained in that circumstance. And so I have electrons that far apart, they have a certain pressure because they're getting hit. And the pressure goes up as I move them closer and closer together because there's more of these photons bouncing between them. There's more impacts. And coincidentally, or as evidence of why this is a better theory, this idea of changing that distance and changing the fact that it has a cycle to it, a frequency, that you're essentially creating a period. And as you go from a distance and you bring it closer to closer and closer, you're creating a period. And so if things were to release, they would release at that frequency. So there's say a resonance frequency between electrons, and everything will start moving at those frequencies, certain distances. And so we know that the electrons in the atom, it's a pretty rigid arrangement. There's the nucleus in the middle with the protons and neutrons, and the electrons have a specific distance from that center. And that specific distance implies a specific pressure between the electrons. And that specific pressure would be time, the amount of time it takes to get for a photon to bounce from one electron to the other electron would be the frequency of the radiation that's going to be produced. So if you want to produce X-rays, you have to compress the electrons. They have to be in the inner rings, let's say, or they have to be in an orbit that has a lot of electrons in it. So they're very close together. But that's the only way you could create an X-ray. And then the visible light spectrum, which is the most common amount of light is produced in that range. That's why we see it, is because there's more of it and it's at the higher frequency. Too high a frequency is just too damaging to cells. So cells can't manage X-rays. That's why we don't see X-rays, is because our body tries to protect us from them, not tries to interpret them. Because they're just, they're too destructive to the cells themselves. But it would be a better form of radiation to be able to see, would be with X-rays, because you get more detail, because they're a tighter frequency, which means higher resolution. So the higher the frequency, the higher the resolution. That's why like radio waves are good for, if you want to just see whether there's mountains or something. It's good for seeing big stuff, but it really sucks at seeing detail. Can't see anything, can't see any details with cannonballs very far apart. You need cannonballs really close together to get the details. So this is an explanation that just you would, it fits everything. It fits the fact that you see different elements produce a different color of radiation. And so that's, electroscopetry or whatever it's called, where every element has a unique signature of radiation it'll produce based on where the electrons are in the orbits and how much pressure they're creating. And so the pressure, the distance between the electrons is essentially dictating what colors each element will produce when you shoot radiation in, when you disturb it and you break it a little bit. Some of that frequency is released. It'll be consistent to what those elements are actually producing as what electrons you're going to affect the most will have a peak, lots of light produced at that radiation, and maybe zero radiation produced at other frequencies. It would be very frequency dependent, little bands of light at specific frequencies. And that's perfectly consistent with this idea that photons really are the energy expressed as charge and voltage with electrons. It's the electron force, photons. Now, there's also a proton force, but that's only seen with magnetism. And it doesn't have a spectrum like the electromagnetic spectrum. So light is called the electromagnetic spectrum. Another thing that I rejected as a kid because they didn't show me any experiments of photons doing anything either electrical or magnetic. You can't bend them with magnets. Why would I call it why would I think of it as a magnetic thing? I can't bend a photon with a magnet. How could it be a magnetic thing? It really can't. It's a force, and forces can't affect forces. So you can't affect a force with a force. You can't hit a photon with a photon. It's an important fact. It wasn't on Feynman's list, but it probably would have been worth saying, that you can't hit a photon with a photon. No good evidence that you can, or any other force. And they have this nonsense, the Einstein lensing nonsense. And I've already pointed out how the Eddington experiment is rubbish. The mathematics is nonsensically rigged. And the galactic lensing images are preposterous when you realize that a gravity lens is the exact opposite of an enlarging lens. A gravity lens bends the light a lot in the middle and bends it very little on the edge. A magnifying lens bends it a lot at the edge and bends it nothing in the middle. Completely reversed. Completely the wrong kind of lens to focus light to make you see something as an image. It's not an image producing lens at all. Gravity. So lots of reasons to doubt this theory that you bend light with any forces. But that's not something Feynman even brushed against that subject. They just assume. And these are all assumptions. And again, Feynman's also famous in these lectures for being the guy who dismissed particle gravity theory it's a substantial problem that needs a solution, but it's not an insurmountable problem. So it's the drag problem. And I've done videos explaining how you can explain how that drag can be overwhelmed if matter is able to capture force that has a directional vector and it captures the force. That is, the force stays inside of it and it keeps pushing it in a direction. And so as long as you can come up with a mechanical mechanism capable of doing that, that doesn't violate conservation laws, you can explain it. So it's not a critical problem. It's not a devastating problem. It's one that if a smart person had spent a little time thinking about it, they could think of a solution. But they didn't want to spend any time analyzing that solution. Instead, they just reached for a bottle of woo, a pretty God of the gaps kind of, there's just a random mechanism. So Feynman doesn't really articulate. He doesn't really like waves as a concept, but he doesn't, so he isn't a big fan of Huygens. He doesn't show the two-slit experiment with a Huygens explanation. He's clearly just used a mathematical explanation. So he doesn't bother with the conventional quantum mechanical explanation for the causes for sine theta, the angle change. So most of the quantum mechanics people say Heisenberg, Huygens, and they use those things to create little wavelets that interfere with each other. Feynman's just saying, screw the waves. All I care about is the fact that there's a probability to where the light goes. Less probability out here, high probability in here. So he just comes up with a mathematical solution, not a causal solution. So it doesn't describe why there's a probability. And he essentially implies that the probability is just magic. That is, a photon travels near the surface of this scissor, and that part of the shadow is fuzzy because the photons might scatter, and out here it doesn't. And that's just a rule, but there's no explanation for why it would matter that the photon went near the surface, and why being near the surface would cause it to deflect to a new location. So he doesn't provide any explanation. And so it's, again, it's pretty weak storytelling, where the story I can tell as a mechanical drawing, I can illustrate it. I can give you the little photons coming at a frequency. I can explain to you how the ping pong ball bouncing between the electrons, more force closer together, less force further apart. Because force, energy, is impacts. Impacts matter. And it explains so much. It explains why the color changes, why the frequency, how the frequency changes, how the frequency is stored, how the atom actually stores more energy by storing more pressure between the electrons, especially on the interior, where you can imagine those electrons can't move out. So any energy that gets in between the electrons and gives them more pressure is, contained by the pressure of the external electrons. And it's a real model, a model that, can go from the beginning, the existence of these things, something, real things, force bits, matter bits. So the force bits are the components of a photon. That's the stuff at a frequency. Gravity is the stuff with no frequency. And magnetism is the stuff, but polarized, not polarized by shift differences, but polarized by a character difference, a charge difference, plus and minus, red, black, square, round, however you want to describe a configuration difference. One is a triangle, one is a square, something, whatever. And magnetism is just segregating out of gravity those two kinds and pushing all of one way and pushing all the rest the other way, and therefore creating a magnification of the effect of the force because you've segregated it. Just as you create a magnet by taking things that are going different directions, pointers, little little magnets going, so that the atoms inside are pointing all kinds of directions and therefore producing a mixed effect. And then when you line them all up, head to tail, head to tail, head to tail, you create a magnet. Completely different mechanism. The unmagnetized steel versus the magnetized steel. The functions, it does something completely different just because you arranged this. You segregated the force. You organized the physical matter, and by organizing it, you strengthened a property it already had. You magnified a property it already had. You revealed a potential it had. All right, so I think that's a pretty good start. And we'll see if anybody has any counter arguments, which probably won't, because it doesn't look like there's much happening here. All right, great topic. EU theories. This isn't electric universe shit. And observations is bringing us back to real classical physics. Well, EU isn't doing that. There's nothing classical about thinking the giant lightning bolts created the frickin' craters on the moon. I mean, you really think that's what happened? That somehow, you know, before we invented cell phones or cameras, that the universe, we had all this, you know, there was giant lightning bolts flying from the Earth to Mars and giant lightning bolts flying all over the frickin' place. Do you really think that was happening? Ugh. So anyway, oh my God, is that Hawaii? Yes, that's what it is. It is Hawaii. Yes, that thing is really, 200 feet high. Lava. 200 feet high lava. And, creating, whatever, 400 square meters per second. It's just, stunning. But, yeah, the wind did shift. It's like exactly the opposite. So it is a little bit interesting to see whether that'll have any effect, whether it might tend to melt one side a little bit more than the other or something. And such. Yeah, well, some of them aren't exactly poor people. So, but yeah, they were a little bit dopey. I mean, I wouldn't have built some of those, building a modest home near a volcano. Yeah, I can see doing that. But some of these houses these people built were a little bit, I mean, that was just stupid. All right, so atom lore, electric universe such as thunderbolts. Well, I think that's the only thing there is thunderbolts. References ancient myth and volcanosca, whatever. Yeah, they do. They reference a lot of smiley face bullshit. They think because they have electrified the universe that now they'll find perpetual energy. And we already have perpetual energy. I mean, we already know where the energy is. And there's like a zillion billion tons of it. This pen can blow up the Earth. Just this pen, if I could release all the trapped photons between all of the electrons inside of this pen, I could melt the Earth. So we already know where the energy is. The trick is getting it the fuck out of there without burning our little fingers or irradiating our fish. That's the trick. So, I mean, this daydream they have that they're going to get like, they're going to put up like a Tesla sale. We'll just stick up our Tesla sale and collect the, charged electrical current and just run everything off the Tesla sale. I mean, it's so frickin' it's juvenile. Not very well thought out, in my opinion. And it's repulsive to my mechanical senses. There's no mechanism. There's no evidence of the charge. See, people keep talking about magnetism too, and it's like, fuck you, idiots. We can measure magnetism. There can't be a special extra amount of magnetism because we can measure it with magnets. You can't fool the magnet. If there's magical extra magnetism here on Earth somewhere being produced, we can detect it. It can't be invisible like gravity, so to speak. I mean, gravity's easy to detect too. I'm just, you can't get much easier than this, right? I mean, that's pretty easy. Pretty easy test you can do. There's no magical other force somewhere. It isn't there, and there's certainly no force that we already know about, because you can say there's dark force. You come up with some new force, but you can't claim the earth is charged or the earth is magnetic, because you already know how magnetic it is, and it's feeble. Its magnetism is feeble, and they use this as it's everything people do pisses me off. I just hate people. They're just so fucking stupid. I'm sorry, but yeah, you're just also damn stupid. Uh, and you iconize, just people just talking. They're talking out of their ass, literally. I mean, they're just farting in your face, and you give them Nobel prizes. And it's really irritating. And then what do you do to me? You just fucking call me names and shit. Anyway, it has explained far beyond the original concept. It hasn't explained anything. So that's just absolute rubbish. There's no explanation for where this charge is held, where it exists, where the energy to shoot a lightning bolt across space, which is a vacuum, electricity doesn't travel across vacuums too well. You have to have electrons, you have a whole bunch of them, which means you have to have a tremendous amount of energy to be able to shoot a lightning bolt through space to another location, because it can't create ions along the way. The atmosphere makes it possible for the charge difference between the surface and the clouds to be discharged. But there's no explanation for how that charge could ever get across to the moon. And again, what makes it possible for the clouds that are just a mile away or less to the surface of the earth is because there's a bunch of matter in the atmosphere and a bunch of ions are created. And that's why the lightning travels that funny path, is because it's traveling the path of the ions it creates. But anyway, I don't want to get into that argument. But I mean, there's just not a shred of rational evidence for lightning bolt universe, that lightning bolts are keeping galaxies together or any of this. It's just no evidence. Nothing. It's silly. All right. Hans Alfred. I mean, again, drop names and it's just a waste of my time. Hans Alfvin is legitimate. Who cares? It's legitimate what? A legitimate idiot. Whatever. I just can't believe you people. You're just so fucking silly. There's no evidence for the foundational explanation that gravity is caused by charge. It's just retarded. Thornhill and those guys do weird crackpot pseudoscience with it. I don't think there's anything about Hans Alfvén that's anything better than Tesla. Okay, and you start wrong premise, you're just going to keep living with your wrong premises. Tesla was wrong. People should just admit it. Okay, he did some modifications to motors that were good. He had some theories of electricity that were okay, but his fundamental baseline theory was wrong. There's no freaking ether and there's no stuff moving through it, except the stuff we can measure. I mean, Tesla just burned holes in the ground with, thinking he could transmit lightning bolts to France. I mean, he actually thought he didn't understand charge. He didn't understand there's no way you can send energy that way because the energy is charged and it's just going to keep plowing into the ground. Anyway, I don't want to get into the whole Tesla thing. That's just stupid. And it's a crappy source of energy for photons in a lot of ways. Unless you do the nuclear thing, unless you release 1 trillion of them at a time, laser beams even, not a lot of energy. The sun, it's only per square meter, 1,000 watts per square meter on the surface of the Earth. It's just not that much energy. But anyway, it's disappointing. So anyway, so I provide a perfectly rational explanation for photons, and these people have to bring up stupid goddamn electric universe shit. Like somehow that had something to do with anything I was talking about. And it really had nothing to do with anything I was talking about. I mean, again, as I'm proposing a unification theory, everything has something to do with everything. But the distance is pretty dramatic between a photon and anything called electricity. Yeah, whatever that is. Rolling on the floor laughing. At what? I mean, what is Thornhill famous for? Is doing a gimmick lecture about general relativity and basically pointing out that Einstein's math only works when there's one body in the equation and blah, 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 blah. And yet, because the equation is basically conceding that gravity is inductive, that it isn't something that comes from nothing. It's caused by uh, acceleration. Acceleration induces it in other bodies. Well, of course, everybody in physics is overrated. So anybody you've heard of is overrated in the sense that their whole theory is fucking, in my opinion, I mean, just grotesquely under evidenced. And Einstein's a perfect example of a completely unevidenced theory. Everything Einstein has proposed in his relativity stuff is completely unevidenced. Okay, we have no real evidence of gravitational lensing, no good evidence. The connection between velocity and breaking clocks can be understood without warping time. So time doesn't have to come into it at all. The fact that measuring devices don't work very well when you move them very fast can be understood as a completely separate argument. It's not dependent on Einstein's mush. So, and outside of that, there's absolutely no evidence besides the connection between velocity and atoms not functioning quite as well. Besides that little piece of evidence, there is none for all of relativity. It's just complete nonsense. And as I've pointed out, the math manipulations to make these arguments about what happens to photons in gravity, I mean, the very fact that they don't apply the inverse square law. So everything else in the universe is affected by the inverse square law in the sense that gravity spreads and the thing can't get hit by the gravity because the gravity is spread. So the gravity spreads as it goes. And so there's less of it to hit this thing. The closer it gets, the more of it hits. The further away it gets, the less hits because the gravity is spreading as it moves away from the body. Somehow a photon breaks that law. So somehow the gravity doesn't spread when it's a photon. Now, that doesn't make any sense. There can't be an explanation, I don't think, for that as anything other than a gimmick. And it's just a mathematical gimmick that cuts in half the possibility of gravitational lensing. So the math would be preposterously impossible for us to ever observe gravitational lensing if it wasn't for that gimmick. And then the second gimmick is even sillier. So not only is it not affected by the inverse square law, they have this idiotic notion that because the photon is moving the speed of light, that it's time dilated. So it thinks from its perception. So even though we watch the photon as an external observer, we see it move the speed of light and go from point A to point B. And we see it do that in 1 second. They argue that the photon thinks it took 2 seconds. So the photon, because of its time dilation, everything's moving slower for the photon. So it thinks it took 2 seconds to get from here to here. And so the photon was affected by twice as much gravity because it thinks it was in the space twice as long. Two preposterous gimmicks. So that's what Einstein's famous for, in my opinion. Now it's just, I didn't realize that they used two silly gimmicks, and those are just silly gimmicks. No reason to believe either one of those two things are true. Absolutely no reason to believe it. All right, does the average person believe that Albert Einstein invented the atomic bomb? Well, he proposed it with E equals mc squared. Clearly, he made it clear that c squared is a lot. So it's a very big number, the speed of light squared. And therefore, matter has a lot of energy in it. So clearly, he was pointing out there's a lot of expansion capacity. There's a lot of heat, a lot of everything you can create with a little tiny atom by expanding it, blowing it up. So clearly, he should be credited because he was the first guy to actually say it out loud, so to speak. Does the average person believe that Albert Einstein invented the atomic bomb? Who cares what the average person believes anyway? I'm not terribly interested. The only people who can fix the average person, who can correct them, help them become unaverage and better people, are the smart people. And the smart people believe all kinds of silly shit, and that's the real problem. Smart people are the assholes of this planet. The dumb people, well, okay, they're dumb. Okay, they didn't bother getting facts. They're lazy. They're uninterested. They're unmotivated. The smart people are motivated enough to read and to understand and to look at the facts and to understand what it is to process information, to understand words like logic and that they have meaning and that facts can't be in contradiction and all that kind of stuff. They're the ones who have disappointed because they're the ones still believing in fairy tales, not even understanding simple rules of evidence, believing things, creating hard conclusions out of soft evidence. They should know that's not the way you're supposed to do science. But, so I'm really angry at smart people. They have no excuse. Dumb animals are dumb animals. You can't blame them because they're dumb. But smart people you can blame. When good robots do bad, there's, you say, why? What, did you forget the rules of logic? Did you, what, what's going to be your excuse? You just wanted a more fun story. I like lightning bolts. They're really cool. So yeah, asteroids, that's boring. Lightning bolts making craters. Yeah, that's really cool. Is that the best you're going to do? I mean, what excuses are going to be for this nonsense? I still can't even. I still can't even fathom why they're so desperate to. Like I said, it has to relate to a Tesla thing. I mean, why are they trying to make the physical interactions between celestial bodies electrical? I mean, when there's just no evidence that it's electrical. There's every evidence that it's gravity and big clumps of shit hit other clumps of shit. So a little lull in the action. Yes, it is a lull. Yeah, I have to stir up some more interest in these these rooms. It's just kind of depressing when you think about it. That a room called Talk Physics, doesn't generate much interest. Disappointing. But again, it is a subject just full of the conventional theory is weakly evidenced and fundamentally full of religious nonsense. I mean, just kind of wishful thinking and wooey forces and magical dark this and antimatter and neutrinos and funny little quirky things, lots of fun little words. And then the tinfoil hatters who say, oh, yeah, that is really wacky shit they're talking. And they start talking shit that's just as wacky. So it was just so bad. I think Elon Musk is, yeah, he's not a bright man. And so, yeah, he's just playing rich man, and just doing oh, this is fun. I'll be the father of something. I'll make people think I'm giving them something. And he's just playing with toys. But he doesn't know. He has no understanding of the theory of anything. He's not a scientist. He's a shameless capitalist and a master of hype. And he's not even a master of it, in my opinion. I mean, he always looks like, in a public appearance, he always looks like a stupid nerd. I mean, he doesn't speak very intelligently. He speaks like a kid talking about shit. I mean, what kind of idiot scientist would ever test a rocket? So you're going to test the engine and put absolutely nothing in the rocket of value. Not do nothing with the the experiment except put an electric car in the driver's seat. For what, called a Tesla, right? An electric car that's called a Tesla. A car that runs on DC electricity, and it's called a Tesla. Yeah. Fuck. I mean, just that the world's just really annoying. Look at that lava glow. Just amazing. Miles. Goes for miles. Miles. So yeah, I wish I could have gotten the. I have to find somebody who has server space on a server that isn't restricted. Because I have server space on GoDaddy and DreamHost, and I couldn't get the Perl script to work on either one. That would allow me to grab the images and recompile them into an animation. It's just kind of annoying. Not that it'd be a very good animation. I mean, 5-minute differences between the pictures isn't going to be a very good animation, but it's better than nothing. A little bit of movement is, interesting. Anthony Bourdain. Is that what, some cook or something, right? Yes, people kill themselves every day, and once in a while it's a famous person. Not that interesting. I mean, the fact that these assholes have kids and then kill themselves, that's a little bit interesting. It's, you're just like, oh yeah, that's first, it's really bad that you're at all a suicidal person. I hate when people do that. Like, they talk about how, oh yeah, when I was a kid I was suicidal, and and then they have kids, and you're like, oh, what? So you think your kid, that can't happen to them either? I mean, it's just so fucking stupid. And it's just really rude to force a kid into the world. And if you want to bail out when they're grown up, that's your business. But when you still got a kid, unless you've got cancer, I don't think you really have a right to take off. He lied about wanting to live for his 11-year-old daughter. I don't know how that even means anything. You lied about wanting to live. Well, then why didn't you lie for a few more years? I mean, 11 is a really bad time to kill yourself. You know, a kid is really, I mean, the teenage years are rough for kids. So if you were going to kill yourself, why didn't you kill yourself when she was 5? Not why do you wait till she's at the most vulnerable years possible to kill yourself? Uh, Whatever. I just don't see, you know, especially people who have some fame and some money. Well, why don't you make a public speech about it first? Why do you kill yourself and just why don't you talk about it and say, look, I'm really having trouble making life mean anything. I got money and I got success, but it doesn't mean anything. And life is, you know, difficult and painful. And, you know, why not point it out and do something useful with your fucking death? You know, but just to write a 5 sentence goodbye note and bail out. This seems way underdone. But there's look, people have crises. You know, they have panic attacks or whatever it is, or some sort of, you know, some neurological moment, some emotional moment, and they end up jumping in front of a car because yeah, they just can't do tomorrow. Tomorrow's too much. Can't do it. Can't do tomorrow. So I understand you can have a crisis and you kill yourself. So I understand that. But you should have things prepared for that. Maybe you should explain to your kid that, you know, I might whack myself because, you know, you know, some days I can't see how to live tomorrow. And if it happens, it's you know, I really care about you and I wanted to be here for you, but I just you know, too many demons in my brain. Too much pain. I mean, everybody can understand too much pain, I think. Not everybody, obviously. It's a ton of people who can't understand pain, but um, mm, yeah, I would understand if my father came to me and said, "I'm in an awful lot of pain and I'm really in trouble." You know, I thought life was simple, but it got really complicated, and my brain just can't do this well. And I'm going to try to be here for you, but I might fail. And just let you know. If I fail, I'm sorry, but I didn't do it because I didn't care. I just did it because I couldn't find a way out. Something like that. I certainly would have understood. But anyway, it's not physics, so I don't know why people need to change the subjects. I mean, you know, I go to the trouble to do this whole introduction to this video explaining what photons are, how it's a huge contradiction to this silly theory they have. This is a nice mechanical model, works very well, fits all the evidence, blah, 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 blah. And then you people want to talk about some freaking news headline. Elon Musk and, you know, Anthony, whoever. I mean, lava is a, you know, meritorious distraction, and it's still really physical. You know, it has a lot of physics in it, a lot of photons flying out of that shit. Uh, so that's a more reasonable distraction. But you know, freaking Elon Musk and freaking cooks, it's not a good distraction. Well, I just mean that I could. The animation I was talking about earlier, I don't know exactly what you mean. I was just talking about the fact that I could run these images. Like if I saved them to my server, I could. Then I could just compile them and have them flip at a quicker rate, you know, and then you could get an idea of how things change over time. I don't think I was talking about any other animations. I mean, the stupid, government, has these cameras, and they have them in crappy locations. First off, I mean, you have like 12 cameras, and they're all pictures of shit, and they only update. They only take a picture every 5 minutes. I mean, it's they could at least make it every minute. I mean, geez. Yeah, well, I should make an animation for a visual aid, but I mean, I think me doing this is pretty good visual aid. I mean, I shouldn't even have to aid you visually, should I? I mean, the idea of saying, oh, so here's two electrons and there's stuff bouncing between them. I mean, I shouldn't have to give you a visual aid for you to understand, oh, close together, more little hits, further apart, less hits. I mean, I shouldn't have to aid you visually. I mean, the visual comparison of seeing photons as some sort of piece of spaghetti gets longer or shorter pieces of spaghetti, or visualizing as bullets fired at a period, with distance time between them. Those are pretty easy to understand differences. Each little bit is exactly the same length, each bullet length, and the only thing that changes is how often, how far apart they are versus, you know, pieces of spaghetti that could be 3 miles long or, you know, 10 nanometers. Shouldn't need a visual aid. So, well, I guess we're stuck with it. Well, it is Friday night, right? Saturday morning, whatever. It's Friday night. So I guess that's one reason why it's a little lower, less peoples and such. I guess I could see how many peoples there are. How many people are there? Let's see. Oh, that's not the right one. It must be this one. 16. Yeah, it's pretty low. Tough luck, I guess. All right, well, I guess I'll title off because I've already done my photon thing, and that seems the purpose of the video primarily. So, and such. So, can't really attract any reasonable critiques. So, we'll just leave it at that. So, till next time and such. Should just leave the volcano thing up. Yeah. Yeah, I guess I could just make a dead room. Yeah, dead room. I guess I should just. I guess I could just keep talking and then you know. But I should. I guess I probably should put lava pictures in the title or something. But I don't think I'll bother exploiting that. But anyway, till the next time and such, and so forth and whatnot. We gotta find some more people and such. Why I open this thing here? Yeah, this one should do it. Oops. All right, there we go. Yeah, do a little bit of fun, just a little bit. Ooh, frequency. It's frequencying. Amazing. No, not really.